Thinking about your next move in chess may be a good analogy to learning about carbocation rearrangements. To stress this point, we'll look at the reaction of two distinct alkenes, one that undergoes rearrangement and the other doesn't. Starting with this one. In this case, there's a tertiary position and a primary position. So when it picks up that hydrogen, the carbocation is going to form on the stable tertiary position. Examining our adjacent positions of the carbocation, we can see that there's not necessarily an advantageous position to move to, where rearrangements could occur, such as moves could occur. None of these put us in an advantageous position. Since favorable rearrangements help stabilize the charge, it's probably not going to outspeed nucleophilic attack. Hence why, with this reaction, we find the chlorine at that position. So let's look at this next example. Ever so slightly different. In this case, we have a primary and a secondary position. So the carbocation would still form on that more stable secondary position than the primary position. However, in this case, we can see that it's adjacent to the ring, allowing for a ring expansion, stabilizing the charge through relieving some of the ring strain. An extremely advantageous move. This expansion of the ring stabilizes the intermediate through increasing its stability, outspeeding nucleophilic attack. However, in this case, we're not done. Another rearrangement will occur, just like in chess, when one advantageous move leads to the next. Since after the ring expansion, it went from a secondary to a secondary carbocation, there is a chance for a 1-2 hydride shift to turn it into a tertiary carbocation through moving it to the adjacent position. And since this rearrangement further increases stability, it will outspeed nucleophilic attack, even if there's two rearrangements before the chlorine attacks.